Here we're going to look at graphing linear equations, ones of special form. Now, special forms doesn't mean that special. For us in this, it's going to mean a variable is equal to a number. So in our previous two videos, which if you haven't seen can be linked, are linked in the description below, we looked at the table method or the finding points method for finding and graphing a line. We also graphed a line using the slope-intercept form. Many times the slope-intercept form doesn't easily fit, or we can't plug in for a specific value every single time. And this is going to happen when the variable equals a number. So if the slope-intercept form doesn't fit or doesn't easily fit nicely, what we're going to do is we're going to turn back to the table method, but do a amended version of the table method. Let's do an example. Let's say we want to graph the line x equals 7, and we want to graph that line on the Cartesian coordinate plane. Obviously, there's no y in this equation. So if I were to try to plug in for x and solve for y, it wouldn't work very well. This also isn't going to fit the slope-intercept form, because if we were to try to get into the slope-intercept form, we'd want a y equals mx plus b. So this doesn't fit the slope-intercept form, and you can't plug in lots of different values for x to find the y. But we can still use a table method. The interesting thing about trying to use a table method is we have to be conscious of what our picks for numbers are. Since we have the line x equals 7, I don't want to pick various values for x. If I plug in a number for x like -2, -2 is obviously not equal to 7, so we're going to get strange things. Therefore, what I'm going to do is I'm simply going to say, because we have x equals 7, no matter what the corresponding value for y is, x is going to have to be 7. So I think of this like plugging in a bunch of different y values and asking, what's the x value have to be with a y value of -2? What's the x value have to be with a y value of 1? What's the x value have to be with a y value of 0? And so on and so forth. Well, what's the x value have to be when y is -2? X has to be 7, because it always has to be 7. So x is 7 when y is -2. X is 7 when y is -1. Let me unbold that. X is 7 when y is 0. X is 7 when y is 1. X is 7 when y is 2. Oops. X is 7 when y is 3. So in other words, x is 7 no matter what we plug in for y. Now that we see what we can do with this table, how we can create this table, we simply graph all these points just like we normally would and connect the dots. Connect those points with a straight line. So we turn to our grid paper, 7, -2 is this point down here. 7, -1 is this point here. I actually didn't do that very well. 7, 0, 7, 1, 7, 2, 7, 3, and you could imagine that no matter what y value we plug in, we always get 7. Now I didn't draw this, and I didn't exactly have my points in the perfect spot. They might be a little bit over to the left or to the right. But what we're getting is a horizontal line, or excuse me, not a horizontal, a vertical line where all of the points on this line have x value of 7. So if we are graphing a line like x equals 7, we end up with a vertical line, and I think about it utilizing a amended version of the table method. A table method where I have to cleverly pick, in this case, my y values so that I don't screw up my x values. So I just simply pick a bunch of y values. X values have to always be 7. That gives me a vertical line. And that's it. So that's how we do the line x equals 7. We can similarly do the same thing with a line like y equals 4. Y equals 4 doesn't have an x value. So some may say, well, it doesn't lend really nicely to the slope-intercept form. You can put it in slope-intercept form, and I'll show you that later. But y equals 4 isn't really nicely put into slope-intercept form. So we can turn to the table method. In this case, since I have y equal 4, I am going to put in different values for x. You don't have to put in the exact same values for x that I'm putting in, but any value for x will give you a y value of 4. So y is always 4, no matter what value of x I input. So if I wanted to put in an 8 for x, y is 4. If I wanted to put a 19 for x, y is 4. I want to put in -316 for x, y is still 4. Y is always 4 in this problem. Now that I have this, I can go graph those points and see what I get. -2, 4 gives me this point. -1, 4 gives me this point. 0, 4 gives me this point. 1, 4 gives me this point. 2, 4 gives me this point. 8, 4 gives me this point over here. And you can see in this case, what we're ending up getting we end up getting a horizontal line where every point on the line has y value of 4. So the graph of y equals 4 is a horizontal line. Let's turn to example 3. In example 3, we are going to graph x equals -3 in the same manner that I did before. Since we have x equals -3, we're going to plug in some different values for y. Any values will work. I'm going to use -2, -1, 0, 1, 2, and 3 for my y values. But no matter what y value we plug in, x has to be -3. And so we get a bunch of points whose x value is -3, and then we can graph those points. Go to our graph paper, -3, -2 gives me this point, -3, -1 gives me this point, -3, 0 gives me this point, -3, 1, -3, 2, -3, 3. We get the picture. We're getting a vertical line where all x values are -3. There we go. Let's do one more example. Here we have 3y minus 2x equals 7y minus 2 times the quantity 2y plus 3. We may say, well, let's try to turn this into slope-intercept form. That's what we did in our previous video. So let's try to turn it into slope-intercept form. When we try to turn this into slope-intercept form on the left side, it has already been simplified. On the right side, we'd use the distributive property. When I take -2 times 2y, I get -4y or -4y. -2 times 3 gives me a -6 or -6. Combining like terms on both sides gives me 3y minus 2x equals 3y minus 6. At this stage, we try to get the y terms on one side. So we would subtract 3y from both sides. If I subtract 3y from the left, that's going to get rid of the 3y on the left, and I'll just be left with -2x. On the right, if I subtract 3y, I will cancel out the 3y and just get -6. And the only thing we can really do is divide both sides by a -2, which gives me x is equal to 3. So x is equal to 3. Just like we've done before, we can plug in any y values that we want. Doesn't matter what I say, what I plug in here. So it doesn't matter what numbers we plug in for y. My x value always has to be 3. Now that we have our x value of 3, we can go ahead and graph this line. I'm not going to take the table with me because we've done this enough. And in fact, sometimes once you've seen this enough times, you don't actually write the table. You just say, oh, that's a bunch of points whose x value is 3. So we just go graph a bunch of points whose x value is 3. So that's all we do. We go graph a bunch of points whose x value is 3. There's 3, 0. Here's 3, 4. Here's 3, negative 3. Here's 3, negative 5. Right, negative 3, negative 8. Any points whose x value is 3. We obviously get a vertical line. That pattern goes on forever. Okay. So a line that is x equals a number or y equals a number graphed on the Cartesian coordinate plane is going to be either a vertical line when it's x equals a number or a horizontal line when it's y equals a number. Now, I want to briefly talk about the slopes of horizontal and vertical lines. Horizontal lines, the ones that were y equals a number, those actually have slope of 0. I'll explain that in a bit. Vertical lines have slope which either does not exist or slope that is infinite. Some places say that the slope does not exist in a vertical line. Other places will say that the slope of a vertical line is infinite. This can be seen in a couple of different ways, but it is explained by the fact that the slope is change in y divided by change in x. Change in y divided by change in x. I've graphed 2 of the lines that we have dealt with already. The line here in blue is the line x equals 3. The line in red is the line y equals 4. Let's focus first on the horizontal line, y equals 4. If I ask you how much change in y there is, well, as you can see, all the points on this line have y value of 4. Therefore, the change in y is 0. So for a horizontal line, the change in y going from point to point is 0. We could have also seen that when we looked at the table. Again, going from one point to the other, how much does y change? Y changes by nothing. So if we have a slope, which is change in y divided by change in x. That top number on a horizontal line is always going to be 0. There's no change in y. And whatever you're dividing by, as long as you're not dividing by 0. So as long as you're going from two distinct points, whether I go from -2 to 0, so my denominator is 2, or I go from -2 to 1, so my denominator would be 3, or if I go from 1 to 2, so my denominator would be 1, all of those lead to a slope of 0. There is another way to see this as well, that horizontal lines have to have slope 0, and that's by thinking through what the slope-intercept form could be in this case. Basically, y equals 4 is the same thing as y equals 0x plus 4. So another way to see that y equals 4 has slope 0 is to think of it as a special case of the slope-intercept form where the slope is 0. So all of that is to say the same thing. Horizontal lines have slope 0. Now let's go to the vertical lines, the ones that were x equals a number. If I have x equals a number, I get a vertical line. Notice going from point to point, the change in x is going to be 0. I go from like 3, 0 to 3, -3, or from 3, -3 all the way up to 3, 8. But the change in x is 0. That was this line here. X equals 3. We got this table. Going from point to point, the change in x is 0 always. So that means the slope, since it is the change in y over change in x, is always going to have a denominator which is 0. And whatever the change in y is, as long as we're going from two different points, it's going to be something. If I take 2 divided by 0, or 3 divided by 0, or 1 divided by 0, dividing by 0 is not allowed. And so in this case, the slope, we say, does not exist. Now, others would also imply the slope is infinite, and that idea, that idea comes from a concept that you may see if you take calculus. In limits of calculus, if you place a numerator, which is a value like 2, and your denominator gets smaller and smaller and smaller, then the corresponding fraction goes out to infinity. So oftentimes people will say the slope is infinite, And that comes from a limit understanding of this ratio here. So some would say it does not exist, others would say infinite. By the way, if you have an equation like y equals 3, or excuse me, not y equals 4, we could manipulate y equals 4 to look like slope-intercept form. However, with an equation like x equals 3, there's no way we can get slope-intercept form to fit here because the coefficient of y in slope-intercept form is 1, and we would have needed a coefficient of y to be 0. So slope-intercept form cannot fit vertical lines. Again, all of that is to say that the slopes of horizontal lines are always going to be 0. The slopes of vertical lines are going to not exist. Or, again, in some places, they would say vertical line has infinite slope. And that's how we graph and understand lines of the form x equals a number and y equals a number on the two-dimensional Cartesian coordinate plane.